So here's a video for Class 9 in Statics. We're going to continue on with Section 3.3, Couples and Force-Couple Systems. The big idea, we're going to do the same thing we did last class. In fact, I'm not sure why we're doing multiple classes with the same thing, but that's totally cool. The idea, we want to be able to simplify systems. They have different forces and moments. We would like to sum them up into create a single force in a single moment. Or sometimes we want to say a force couple, an equivalent force couple that can be placed onto an object to represent all of the forces and all of the moments that are being placed onto the thing. Now this is actually what we're talking about here. What I'm showing on this screen and in my notes, it actually comes up into the next class. So we don't necessarily need to spend too much time working on here. We'll mention it and then it'll come up again in the next class. Right? The idea in this that we're going to see here is that we could take a bunch of different forces that are being placed onto something, and we can figure out the force couple system that would represent to be the equivalent thing, and then we can then later find a particular spot where we could put that force, that single force, that would not only represent the force but also would create the moment that all those other things. So we have like a whole bunch of different forces acting onto this thing, and we can condense it down into a single force that's at a particular location that would represent all the work going on there. The one on the left here, they mentioned that they note that like if the forces happen to all be concurrent, that is, their line of action, all of them happens to merge in one spot, then that force can be, then you get a single force acting exactly at that spot. That's the idea. But and then they also refer to something as a wrench, which I think is sort of like this weird thing. But they're saying that you could apply that equivalent force system right there and put it into one particular place and pretend like a wrench is acting right onto that thing. So these are all those same things, and they're kind of a little blurrier than they should be right here. But a wrench is the simplest system that could represent any general force in a couple system. But we're going to do that in the next class. So it wasn't necessarily something that we had to do right here. But here's an example. It's hard to read from the mixed up, muddled up stuff that's here on this page. Boom, 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 boom. And I think that ends up being in class 10, that previous stuff. So class 9 is what we're dealing with. And so here are a bunch of forces that are acting on this piece. And we want to replace this force, replace the force and couple system shown by an equivalent resultant force and couple that acts at point O, right? So in this case, they're telling us the location where they want it to go. So this is a worked out problem from Hibbler. It's one of the example in their book. I think it's example 4.14. I can't tell, the numbers all screwed up there. Now here's the basic idea. Break this thing into components. Break these forces into components and then figure out what kind of moment each of them is going to make. Well, first off here, we also want to do an equivalent force, right? So we need to do a force summation. And once again, this is not a free body diagram. We're not finding the reactions. We're finding the equivalents, aka the resultant force that would be placed onto this thing. So we got 3 kilonewtons and this 5 kilonewtons and this 4 kilonewtons. We resolve them into the x and their y's, and then we sum up all of the x and y components, right? So we sum up the x component here, the x component there. There's no x component into this 4 kilonewton thing here. And we find that we're going to have a resultant force, right, of this plus this. So this is what is going to happen onto the piece. And then in the y direction, the same thing. Make sure you get the signs the correct and broken thing down. And we can see that we have a 6.5 kilonewton force acting downward. Oh, excuse me. So if you want to find the magnitude, we get the magnitude of it with the Pythagorean theorem there, and we can also get what the angle is going to be with respect to the horizontal. So it's just going downwards like that way right there, right? And that's the angle that the thing's happening on. And remember, this is just what all of these forces are doing, and we're just saying, okay, well, take all those forces and we're going to put them at O. But now we also want to have the moments, right? So this is a separate thing that we want to do. So honestly, I think it would be better here if I pause for a second and move that figure over 1 second. Okay, here, so I made sure I got this figure. We want to make sure we get the figure onto the page there as we try to narrate how this is all going on here. So we're going to find the equivalent moment. Remember, we're not getting the sum of the moments. This is not the equilibrium here. We're not using the free body diagram. We're just trying to figure out what an equivalent moment right here would be to all the things that are taking place. So we break this apart right here. We take the 3 kilonewtons right here, and we figure out that's the vertical one right there. We can see that we treat it as positive because it's counterclockwise, and then we take the distance right here that it's going, and then we do the same thing for the horizontal component, but it's negative because that one is making a clockwise motion, and the distance right there is 0.1. We want to do the same thing here for the horizontal component right here, but this one's going to be positive because it's going counterclockwise about O, but it still has the same distance because they're symmetric right there. And then we want to take this 4/5, and this one too is clockwise, and that's down to 0.5 because it's these two added together. And then lastly, we're going to get this guy, and his 2 is also clockwise, and his distance is our 0.2. So looking through all that, we end up with this negative. That means that it's overall it's a clockwise moment of 2.46 kilonewton meters. So here's the summary, and should be the thing that we key on. That's the bottom line. That's the big idea right there. That we just took all of these forces that are happening up here, right, and we condensed it down into a single force couple system. Realize that the resultant force and couple moment will produce the same external effects or reactions at the supports, right? So if we wanted to find the reactions, they would be equal and opposite to what we just found, because what we're doing is we're finding equivalent forces and moments right now. So here's another problem where we have the structural member that's subjected to this couple, right? So it already has a couple being placed on it, and it's being represented by this right here, right? And they're showing, I believe that this 3, 4, 5 is trying to show us the orientation of the couple. And there's also got forces also. So there's a couple moments that they're representing in this manner right here, and then there's a force F1 and a force F2. And it looks to me like that force F2, we got to see which direction they're saying that's going to go in. I'm not 100%. Well, I guess they're saying it's going along this diagonal right here. It's passing along that point B. That's really kind of a hard way for them to express that. But anyway, okay, so 2 forces in a moment, and we want to try to reduce this, right? So they're doing it via vectors, which works out pretty well in this case. Yeah, okay, so what are they doing with this U thing going on here? They're saying UCB. I guess they're saying that they're creating a direction. Yeah, that seems what they're doing. They're saying that there's a line that's running like right along there, and so that's what they're doing. Yeah, okay. So they're taking the length between here and here. That's that RCB. So here's the vector and here's the length. Okay, so they're taking that 300 newtons and they're turning it into a vector, right, by way of the orientation as shown. So now we've written out what F1 is, and now they've written out what F2 is. They also, we've written out what M is. This is the moment that's being applied, and it's an external moment couple that's been applied to here. So what they've done is they just took the sum of the forces. It's going to be the resultant force, and they just took the I, the K and the I and the J right here, right? So there weren't any others. There's one for each. That was nice of them, right? So there you go. That's going to be the resultant, and so that's what that's going to look like. All right, we're going to place that down there at the base because that was what our goal was. And now we do that was the force summation, and now we do the moment summation. And so one thing we're going to have, there's a number of things taking place here. We're going to have the moment that was already on here, so that's the external moment on here. But now we're going to need to move this force 1 right here down to here. And I don't think anything is going to happen there, because you notice that if you were to take the vector RC is going to be exactly in line with F1. So it's not really going to create a moment. This force passes right through the point about which we're doing the thing. So I think later on they show that right here. Yep. We're going to take and cross K against K, and you're going to get 0. And then they do the same here with the same concept here, where we take this position vector, which went up and over to there, and we had previously found what the force 2 vector was in. So we take them cross against each other, and you could see that we're going to take the determinant of this matrix, and then we're just going to add all the i's and all the j's, and this is going to be what the moment is. And we could even we could even show that as being a new couple. So this is a force couple system that represents this original loading right here. And the big idea, here's the big light bulb coming on. The big idea is that all we're doing is trying to represent an equivalent system, an equivalent set of forces and moments. If we have them all located in a bunch of different places, we want to move them to a particular spot. This is all we've done. So that's the pitch for today, and we'll go and move on to examples.